So yesterday, again, we talked about the completely randomized design. It is the simplest experimental design. However, it can lead to some flaws. Part of designing an experiment is to be familiar with any factors that could influence your results, whether they be randomized, controlled, or manipulated. And if your population is not homogeneous or if it's not similar, it will be difficult to know if your results are due to the different treatments or the differences in your population. So that's why rarely will you have a population that is actually very similar. So completely randomized design isn't always going to work. But these next two experimental designs have ways to minimize the effect of some of those outside factors that you can't control. So today we're going to talk about it's called the matched pairs design. There's kind of two ways to think about it. So the definition is just when we have our experimental units paired up, hence matched pairs. And the way they are paired is by something that they have in common. So you compare two females together, two males together, or anything that you think could be a factor that could change your outcome. You would put two people that have those similar factors in common. So paired by something in common. And then when you pair them together, one person in your pair would get one treatment, the other one would get the second treatment, and then you compare the results in each pair. So one treatment per person in pair, then compare. Okay, so again, you take your population, and in that population you create pairs based on something that your population has in common, or the pairs have in common, and then you split up the treatments between the individuals in your pair. So what populations does it work best with? What population does it work best with? Is when you are actually able to pair up your experimental units. That won't always be the case. And since it is matched pairs, that means you are limited to only being able to do two treatments. So your experiment has to also lend itself to matched pairs. Okay, so there's kind of two different ways to look at this matched pairs design. One is where each pair consists of two different individuals, so you match them up, subject 1, subject 2, one person gets the treatment, one person has a control or like a placebo, and then you compare the results after, and you do that for each subject, and you only compare within the pair. Okay, so that's one where it's two different people, one person gets a treatment, one person gets a control. Or matched pairs can also look like where each pair, the pair is like a before and after. So you're dealing with just one individual, but they're kind of paired with themselves. So you could do like the pre and post test, or like a before and after. So another option for the matched pairs, gentlemen. Sure. Another option for matched pairs is to have one individual and give them the treatment and the control, and then compare the results after. And when you're doing that option, then you can do one comparison at the very end where you look at all of the results. It doesn't make sense to do that big comparison at the end with the one with two individuals, because the reason we're pairing them up is because we think that these two have some different factors than these two, which could affect the results. So comparing across pairs here doesn't make sense, but when it's just you being compared to yourself, one individual at a time, you can do the big comparison at the end. Okay, so again, main thing is either two individuals, one person gets one treatment, the other one gets the second, or it's like a before and after with one person. Okay. So how to randomly assign experimental units to treatments in the matched pairs design is going to be similar to how we assigned the treatments yesterday with the completely random. So first you're going to determine your pairs. That you have to do. It can't be random because, again, we're pairing based on something they have in common. So you do have to create the pairs. And remember, each pair needs to have something in common, or some factor in common. And then within the pair, you need to decide who's going to get like the treatment and who's going to get the placebo, or who's going to get what treatment. So you're going to randomly assign treatments. You can do it just by flipping a coin because that's random, or you can use your calculator to choose the random integer from 1 to 2. Okay, so again, when you are assigning the treatments to the individuals in the pair, it does have to be random. You can't choose who gets what treatment. So this one is for the first option when you have two individuals and one person gets one treatment, the second person gets a second treatment. This number 3 here is if you're doing the before and after option. So if you're doing like the pre-post test or the before and after experiment, you would first, because the before or the pre part, you have to collect data from your individuals first. So collect the pre or before data. Then you would apply whatever the treatment is that you're testing. And then you would gather data again. This would be like the post test or the after. Okay. So now so moving on to this last design in the note packet. So this one is called randomized block design. It's basically the larger version of matched pairs. So with matched pairs, you grouped two people that were similar together, but then you had the limitation of only being able to use 2 treatments. With randomized block design, it allows you to group together more similar experimental units together into blocks, so you can have bigger groups, and then randomizing the experimental units within each group to get the different treatments, called blocking. So this one is a little bit more involved than the other 2 that we've been working with. So each group, when you divide up your first groups into something that they have in common, so like males and females, those are called blocks. And then within the block, you're going to randomly assign the treatments. And doing these blocks, again, can help minimize the amount of confounding variables. This is when the effect of 2 factors on the response variable cannot be distinguished. So like those randomized factors, things that could affect the outcome of your experiment, but you can't control. Doing these groups by something they have in common can help minimize the effect of those randomized variables on your response variable. All right, so the definition, randomized block design, is where you divide your population into blocks something they have in common. So like males and females are popular blocks, or doing by like age ranges, or just anything that they have in common, kind of similar to the idea of stratified sampling, how you have to have groups with something in common, kind of the same idea here. And then within each block, the experimental units are randomly assigned to each treatment. So this part is kind of like the completely randomized experiment that we did on yesterday. So you divide them into groups, and then you're doing separate mini experiments basically in each block. Okay, so what populations does the randomized block design work best with? This is when, if you have the heterogeneous populations, or populations that are different and they're not all the same. So when your population is made up of individuals whose differences may affect outcomes or results. And when you're assigning your blocks, it is helpful if you have the same number of individuals in each block, but it's not necessary. So like, for example, with the one below, when we split it up into males and females, if you just don't have the same number of males and females in your experimental units, that's fine. It's just something that's recommended, but if it can't happen, that's okay. All right, so what it looks like with our diagram here. So you start with your subjects, all your experimental units, and then you split them up into groups. So you do this. You split them up by some similarity. So in this case, it was gender. So that's one thing you get to choose. And then within each group, or within each block, you're going to have to split it up into groups based on how many treatments you have. So the number of groups is the same as the number of treatments, just like the completely randomized one yesterday. And so just like yesterday, you use your random integer generator to create those different groups. So to put the individuals into those different groups in each block, you use your random integer on your calculator, and then randomly assign the treatments, like we did yesterday as well, also with your random integer generator. And then finally, you would compare within each block. So to write this out in words, so how to randomly assign experimental units to treatments in, oh, this says matched pairs. This should say randomized block. Sorry about that. So you're going to first divide your population into blocks, again, based on some similar characteristic. Based on something they have in common. And usually that something is a factor that could affect your results. So if you think men and women are going to have different like reactions to a drug, then splitting them up into blocks with males and females would make sense. Okay, then you are going to use the random integer generator in your calculator. Let's do rand int in the calc. Just as you did yesterday with the completely randomized design, to assign the experimental units to their groups and then the treatments to those groups. Okay, so down here I kind of stressed this yesterday, but one note about the relation between a designed experiment and random sampling. It's often the case that experimental units are selected to participate in a study are not randomly selected because sometimes we often need the experimental units to have some common traits. Like if we're testing a drug to see how it affects depression, then the people in your experiment have to have depression in order for that to be a valid experiment, so it can't always be random. So for this reason, participants in experiments are recruited or volunteer to be in a study. However, once we have the experimental units, then we can use our randomness to assign them to groups and assign them to treatments. So it's a little bit different how the random comes into play. All right.